Today we will learn about multiple comparison tests. Our learning objective is to understand the definitions used in multiple comparison tests. We also want to determine which means are differ using the multiple comparison test if the null hypothesis is rejected in the Kruskall-Wallis non-parametric ANOVA. Our learning outcomes is to make inference to related sample using this multiple comparison test. We use multiple comparison tests when a hypothesis testing procedure such as Kruskall-Wallis test leads us to reject the null hypothesis. This means that not all sample populations are identical. Multiple comparison tests are used to answer the question which populations are different from which others. This is our past example from Kruskall-Wallis, that is example 6.2. As we can see that we reject H null at the level of significance since our test value is greater than our critical value. Hence, there is enough evidence to support the claim that is the three populations represented by the data are not identical. Since we reject H null, we must continue with multiple comparison tests to see which populations are different from which others. When we apply this multiple comparison procedure, we use what is known as experiment-wise error rate. The experiment-wise error rate, which represent a conservative approach in making multiple comparisons, holds the probability of making only correct decisions at 1 minus alpha when the null hypothesis of no difference among populations is true. Our first step is to obtain the mean of the ranks for each sample, and let R bar I be the mean of the ranks of the I sample and R bar J be the means of the rank of the J sample. Next, we select an experiment-wise error rate of alpha, which we think of as an overall level of significance. Our choice of alpha is determined in part by K, where K is the number of samples involved and is larger for larger K, which means there are two conditions that we must fulfill to choose our alpha. If we have K samples, there will be a total of pair of samples that can be compared a pair of times. We usually select a value of alpha larger than those customarily encountered in single comparison inference procedures. For example, we take alpha equal to 0.15 or alpha equal to 0.2 or alpha equal to 0.25 depending on the size of our K. Next, we find the value of Z in the table A.2 that has alpha over K, K minus 1 area to its right. And finally, we form the inequality. There are two types of inequalities in this multiple comparison test. The first, if the K samples are all of the different size, we will use inequality 6.7, where N is the number of observations in all samples combined. Second, if the K samples are all of the same size, we will use inequality 6.8. Any difference modulus R bar I minus R bar J that is larger than the right-hand side of inequality 6.7 or inequality 6.8, if applicable, is declared significance at the alpha level. Now we will continue from our past example, that is example 6.2, since we have rejected the H null. The first step is we must do the hypothesis. Since we have three groups of populations, we must make three difference of hypotheses. To make all possible comparisons in order to locate where the differences occur, let's choose an error rate of alpha equal to 0.15. In this example, To find the total comparison that we want to compare, we will use these equations. So, in this example, we will have 3 comparisons to make. From table A.2, we find that the Z value with 0.025 of the area to its right to be 1.96. To get the mean of the rank for the 3 sample, we will take, for example, the sum of R1, we will divide by its total number of R1 so that we will get R bar 1. We will apply this step to R bar 2 and R bar T. From this table A.2, to find the value of Z, first we have equation alpha over k minus 1. That is equal to 0.025. As we know, the half value under normal distribution curve is equal to 0.5. Then, we have to minus 0.5 with 0.025, and we will get 0.475. From the table, we find that the value of 0.475 is 1.96. Now, we want to compare within 2 groups. First, we compare group 1 and group 2. As we can see that our test value is greater than our critical value. Then, we compare group 1 and group 3. We also see that our test value is also greater than our critical value. And last, we compare group 2 and group 3. Here we can see that our test value is smaller than our critical value. Now we want to make decision. Our first decision is to reject the H null since our test value is greater than our critical value. Hence, this comparison is significant. Our second decision is also to reject the H null since our test value is also greater than our critical value. This comparison is also significant. And our last decision is do not reject the H null since our test value is smaller than our critical value. Hence, this comparison is not significant. Our conclusion, first, there is enough evidence to support the claim that there are differences between median group 1 and 2. We conclude that subjects for elective caesarean section before the onset of labor tend to have lower cortisol levels than women experiencing induced labor at emergency caesarean section. Our second conclusion is that there is enough evidence to support the claim that there are differences between median group 1 and 3. We conclude that the women in population 1 also tend to have lower cortisol values than the women in population 3. And our last conclusion is that there is not enough evidence to support the claim that there are differences between median group 2 and 3. We cannot conclude that the population represented by samples 2 and 3 differ with respect to their median cortisol level. Here are a few exercises that you can try to improve your knowledge about this chapter.